Tonight, you are going to put something down and watch it fall. You won't think twice about it. A cup slips from your hand, a phone drops from a table, rain falls from the sky, and your brain quietly files all of it into the same category. Gravity. Simple. But the real answer is far stranger, because there is a possibility that gravity is not a force at all. For centuries, gravity seemed obvious. Objects fall down. Planets orbit stars. The moon circles Earth. Something must be pulling on everything else. Right? That idea feels so natural that it becomes invisible. Yet some of the smartest people who ever lived eventually discovered that the universe may not work that way. What if nothing is actually pulling anything? What if the feeling of gravity is really something else entirely? To understand why that question matters, you have to leave your living room and travel back a few hundred years. Imagine standing beneath an apple tree in 17th century England. According to the famous story, an apple falls and catches the attention of Isaac Newton. The story has been exaggerated over time, but the insight behind it was real. Newton realized that the same thing causing an apple to fall might also be controlling the motion of the moon. That was a radical idea. Before Newton, the heavens and earth were often treated as separate realms. Newton connected them. One set of rules, one universe, one invisible force acting everywhere. His equations were astonishingly successful. They predicted planetary motion. They explained falling objects. They helped humanity navigate oceans and eventually launch spacecraft. For more than 2 centuries, gravity looked solved. Case closed. But there was a problem hiding in plain sight. Newton could describe gravity perfectly. He could calculate it. He could predict it. Yet he could not explain what it actually was. How does Earth reach across empty space and pull on the moon? How does the sun influence planets millions of kilometers away? What is doing the pulling? Nobody knew. Even Newton found the idea mysterious. Then, in the early 20th century, a young patent clerk named Albert Einstein began rethinking everything. Einstein noticed something strange. Imagine standing inside an elevator. Suddenly, the elevator accelerates upward. You feel heavier. Your feet press against the floor. Now imagine standing still on Earth. You feel that same pressure. The sensations are identical. That observation became one of the most important clues in scientific history. Einstein called it the equivalence principle. In simple terms, acceleration and gravity can look exactly the same. That sounds innocent. It wasn't, because once Einstein followed that idea to its conclusion, gravity stopped looking like a force. Instead, it started looking like geometry. The universe suddenly became much stranger. Picture a stretched rubber sheet. Place a heavy bowling ball in the middle. The sheet bends downward. Now roll a marble nearby. The marble curves toward the bowling ball, not because the ball is pulling it, but because the surface itself is warped. This analogy is imperfect, but it captures the basic idea. According to Einstein, massive objects bend space and time around them. Planets move through that curved landscape. Moons move through it too. Even light follows those curves. In this picture, Earth is not pulling you downward. You are simply moving through curved space-time. The path you naturally follow happens to lead toward the planet. Gravity becomes a consequence of shape rather than force. That sounds almost impossible. Yet the evidence kept piling up. One of the earliest tests involved starlight. Einstein predicted that light passing near the sun would bend. According to classical thinking, that made little sense. Light has no mass. Why would gravity affect it? But if space itself is curved, light would naturally follow those curves. In 1919, astronomer Arthur Eddington measured the positions of stars during a solar eclipse. The result supported Einstein's prediction. Suddenly, the impossible idea looked real. Space was not an empty stage. It was part of the story. Over the following decades, scientists discovered more evidence. Clocks tick differently near massive objects. Light changes energy while escaping gravity. Entire galaxies bend light like giant cosmic lenses. Every successful test pointed in the same direction. Einstein's description worked remarkably well. So gravity was solved again, or so it seemed, because another problem emerged. Actually, several problems. Modern physics rests on two extraordinary theories. General relativity describes gravity. Quantum mechanics describes the tiny world of particles. Both theories are incredibly accurate. Both have transformed civilization, and both refuse to cooperate with each other. When physicists try to combine them completely, the